There is a version of science that has everything figured out. Clean equations on a whiteboard, confident textbooks, a tidy story of how the universe works. That version is a lie. The real story is stranger. It's a story where we've mapped billions of galaxies but cannot name what most of the universe is actually made of. Where two of our best telescopes agree on a measurement that our best theory says is impossible. Where we've detected signals from space that nobody can explain, found structures so enormous they shouldn't exist, and stared into the sky on a clear night, not understanding something as basic as why it's dark. That alone is worth sitting with. You don't need a doctorate to grasp it. Go outside on a dark night, look up, and think about this. If the universe is infinite and packed with stars in every direction, the sky should be blindingly white. Every line of sight should eventually end at a star. Instead, it's black. Why? That question has been puzzling astronomers for centuries, and the answer turns out to say something profound about the universe's age and structure. It's also just the beginning. This is called Olbers's paradox, named after the German astronomer Heinrich Wilhelm Olbers, though the question was being asked long before him. The logic is simple. If the universe is infinite and has existed forever, and if stars are scattered throughout it without end, then every direction you look should eventually terminate on the surface of a star. The sky should be as bright as the surface of the sun, a wall of light in every direction. Instead, it's dark. The resolution to this paradox is more unsettling than the puzzle itself. The sky is dark because the universe is not infinite in age. It had a beginning. Light from stars billions of light years away hasn't had enough time to reach us yet. The universe is only about 13.8 billion years old, and the observable bubble of it we can see is limited precisely by how far light has traveled in that time. Beyond that boundary, light exists that we will never detect. From galaxies we will never know. But there's a second layer. Even within the observable universe, the expansion of space is stretching the light from distant galaxies, shifting it out of the visible spectrum into infrared, invisible to our eyes. The darkness of the night sky is not an absence of light. It is a consequence of time, distance, and the redshifting of a universe that has been stretching since its beginning. A simple observation. An answer that contains an entire cosmology. The standard model of cosmology says the universe began roughly 13.8 billion years ago, in an event we call the Big Bang. A moment when all matter, energy, space, and time erupted from an extraordinarily hot, dense state and began expanding. We can trace the universe backward to a fraction of a second after that moment. We cannot get to the moment itself. Here is why this is so uncomfortable. General relativity, our best theory of gravity and space-time, breaks down at the precise instant of the Big Bang. The equations that work beautifully everywhere else in the cosmos produce nonsense at the very point of origin. They spit out infinite density, infinite temperature, a singularity, which is physicists' shorthand for "we don't know." Asking what happened before the Big Bang using the tools of general relativity is like asking what's south of the South Pole. The concept of before may not apply when time itself began at that moment. Several frameworks have been proposed. Inflationary cosmology suggests our Big Bang was one of many. That a larger, churning quantum field spawns universes perpetually, each one a bubble of inflation that produces its own space-time. In that picture, our universe has no ultimate beginning. It's one event in an eternal, self-generating process. String theory offers the notion of a cyclic universe, bouncing big bangs in sequence, each one inheriting a faint signature from the one before. The problem is that none of these ideas are currently testable. We cannot reach beyond the cosmic microwave background, the oldest light in the universe, emitted roughly 380,000 years after the Big Bang, and whatever occurred earlier is, at least for now, beyond observation. The origin of everything remains precisely a mystery. In the 1970s, astronomer Vera Rubin was measuring how fast stars orbit around the center of galaxies. Physics predicts that stars far from the galactic center should move slowly, the same way outer planets orbit the sun more slowly than inner ones. Instead, Rubin found that the outer stars of galaxies were moving at roughly the same speed as the inner ones, or even faster. Something was holding them in orbit that wasn't visible. The conclusion was that galaxies are embedded in vast halos of invisible matter, matter that doesn't emit, absorb, or reflect light, but does exert gravitational pull. This substance, which we now call dark matter, makes up about 27% of the total mass energy content of the universe. Everything we can see, every star, planet, galaxy, and nebula, accounts for only about 5%. The rest of what we call ordinary matter is dark. Decades of searching have failed to directly detect a single dark matter particle. Enormous underground detectors filled with liquid xenon, like Xenon 1T in Italy's Gran Sasso laboratory and its successor, Xenon NT, have waited patiently for a dark matter particle to knock into an atomic nucleus. The LX Zeppelin detector in South Dakota, the world's most sensitive as of 2023, has found nothing. The Large Hadron Collider has looked for signatures of it in particle collisions through missing energy signatures. Nothing. The leading theoretical candidates, particles called WIMPs, or weakly interacting massive particles, have repeatedly failed to show up where models predicted they would. Each null result doesn't rule out dark matter, but it does squeeze the parameter space into increasingly specific corners. A rival candidate, the Axion, is currently being searched for using electromagnetic resonance chambers. The Axion Dark Matter Experiment, ADMX, and newer designs are beginning to probe the ranges where axions are theoretically best motivated. Other candidates include sterile neutrinos, primordial black holes formed in the early universe that could have persisted to the present day, and even fuzzy dark matter, ultralight particles with quantum wavelengths spanning kiloparsecs, which would produce a different texture of small-scale structure than cold dark matter. We know dark matter is there because without it, galaxies would fly apart. We can map its distribution using the way it bends light through gravitational lensing. We just don't know what it is. After half a century of searching, that remains one of the most embarrassing gaps in all of physics. If dark matter is humbling, dark energy is staggering. In 1998, two independent teams of astronomers studying distant supernovae made a discovery so unexpected that it won the Nobel Prize 13 years later. Not because it answered something, but because it made everything more mysterious. They found that the universe's expansion was not slowing down under the influence of gravity, as everyone assumed. It was speeding up. Something was pushing space apart at an accelerating rate. Something with energy but no apparent source, no identifiable particles, no mechanism anyone could describe. It was given the name dark energy, and it makes up roughly 68% of the total energy content of the universe, which means that about 95% of the universe is made of things we cannot identify, detect, or explain. The leading hypothesis is that dark energy is a property of empty space itself, a kind of built-in repulsion that Einstein originally proposed and then called his greatest blunder, and which turns out to be real after all. But quantum field theory, when asked to calculate the energy density of empty space, produces a number roughly 10 to the power of 120 times larger than what we actually observe. That discrepancy is the largest mismatch between a theoretical prediction and a measurement in the history of science. In 2025, the Dark Energy Spectroscopic Instrument, a collaboration involving dozens of research institutions worldwide, announced new evidence suggesting dark energy may not be constant. It may be changing over time. If confirmed, that would invalidate the cosmological constant model entirely and require a completely new theory of the universe's evolution. The nature of dark energy remains wide open. Two of the most powerful telescopes ever built are both correctly measuring how fast the universe is expanding. The problem is they get different answers. And the gap between those answers has been widening for a decade. The Hubble constant describes the universe's expansion rate, how fast galaxies are receding from us per unit of distance. One way to measure it is to look at the cosmic microwave background, the faint glow left over from the early universe, and use the standard cosmological model to calculate what the expansion rate should be today. That method, using data from ESA's Planck mission, gives a value of about 67.4 kilometers per second per megaparsec. The other method involves using distance markers, Cepheid variable stars, and Type 1a supernovae as a cosmic ruler to measure the expansion rate directly from nearby galaxies. That approach, used by Nobel laureate Adam Rees and his SH0ES team, consistently yields about 73 kilometers per second per megaparsec. The difference sounds technical, but it represents a significant contradiction in the physics that is supposed to describe the universe. For years, many astronomers suspected the discrepancy was a measurement error. In 2024 and 2025, the James Webb Space Telescope independently confirmed the Hubble measurements to high precision, effectively ruling out telescope error. The tension is real, as Rees put it. What remains is the real and exciting possibility we have misunderstood the universe. Possible explanations include a new form of early dark energy that gave the universe an unexpected push after the Big Bang, unknown exotic particles, or a flaw in the standard cosmological model itself. None have been confirmed. The universe seems to be expanding at a rate it isn't supposed to. This is the most fundamental question in all of science, and possibly in all of philosophy. When the Big Bang occurred, matter and antimatter should have been produced in equal amounts. For every proton, an antiproton. For every electron, a positron. When matter and antimatter meet, they annihilate each other in a burst of pure energy. If the early universe had been perfectly symmetric between the two, everything would have cancelled out and the universe would contain nothing but radiation. Instead, there's a universe. Galaxies, planets, people, all of it. This means that somewhere in the first moments after the Big Bang, matter slightly outnumbered antimatter by about 1 part in a billion. That tiny imbalance survived the mass annihilation, and everything we see today is the remnant of that surplus. Why the imbalance existed is unknown. Physicists call it the Baryon asymmetry problem. Sakharov's conditions, laid out by Soviet physicist Andrei Sakharov in 1967, describe what would need to be true for such an imbalance to arise, including a violation of a symmetry called CP symmetry, meaning the laws of physics behave slightly differently for matter versus antimatter. That violation does exist in the standard model, but not nearly enough to account for the surplus we observe. Something else must have tipped the scales. We have no idea what. The universe's existence is, by current physics, slightly miraculous. The Big Bang by itself doesn't fully explain the universe's large-scale structure. If you look at opposite ends of the observable universe, regions so far apart that light has never traveled between them, they have nearly identical temperatures. This shouldn't be possible unless they were once in contact with each other and reached thermal equilibrium. They were, but only if space expanded far faster than the speed of light in the universe's earliest moments. This is the theory of cosmic inflation, that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, stretching a region smaller than a proton to something the size of a grapefruit, or possibly much larger, in a vanishingly tiny sliver of time. Inflation solves multiple problems simultaneously. It explains the uniformity of the early universe, the flatness of space, and the origin of the large-scale structure of galaxies we see today, which grew from quantum fluctuations stretched to cosmic scales during inflation. The problem is that we don't know what caused inflation or what ended it. The theory requires a field, usually called the inflaton field, that dominated the early universe and then decayed into the matter and energy of the Big Bang. No such field has been detected. Dozens of inflationary models exist, proposing different kinds of inflaton fields with different properties. Most produce universes broadly consistent with what we observe. Most also predict the multiverse, that our Big Bang was one of many, with inflation continuing elsewhere and spawning other universes perpetually. Testing inflation directly requires detecting gravitational waves from the inflationary epoch, faint ripples imprinted in the polarization of the cosmic microwave background. Experiments like the Simons Observatory are now beginning to reach the sensitivity needed to look for them. The observable universe, everything within 46 billion light-years of Earth, is all we can directly access. Beyond that boundary, space exists that we cannot see because light from those regions has not had time to reach us. But how large is the universe beyond that boundary? Is it infinite? We genuinely don't know. The geometry of space, measured through the cosmic microwave background, appears to be flat, meaning parallel lines remain parallel, and the angles of a giant triangle add up to 180 degrees, as in ordinary Euclidean space. A flat universe is consistent with being infinite, but it's also consistent with being unimaginably large but finite, like the surface of a sphere so enormous that our observable bubble sits well within a region that looks flat. If the universe is infinite, then by probability, every possible configuration of matter repeats infinitely many times. If the universe is finite, it might have a shape, perhaps a three-dimensional torus or some other topology that would cause distant light to appear more than once from different directions. Cosmologists are actively looking for evidence of such topology in the microwave background. So far, nothing definitive. The universe's outer limits remain one of the great unknowns. On the night of August 15th, 1977, the Big Ear radio telescope at Ohio State University detected something extraordinary. Astronomer Jerry Eman was reviewing the overnight printout the next day when he found a sequence of numbers and letters that indicated a signal of stunning intensity at almost exactly 1,420 megahertz. The frequency at which hydrogen atoms naturally emit radio waves. This is the frequency SETI researchers had long designated as the most logical channel for an interstellar broadcast, because hydrogen is the most abundant element in the universe, and any technological civilization would likely know its signature. The signal lasted 72 seconds, precisely as long as the telescope's beam took to sweep past the source. Its intensity was 30 times stronger than the background noise. It had all the characteristics that SETI scientists had said an alien signal would have. Eamon circled it on the printout and wrote one word in the margin. Wow! It has never been detected again. Dozens of follow-up observations of the same patch of sky have found nothing. A hypothesis proposed in 2016 suggested it came from a passing comet, but the geometry didn't hold up. In 2024, a team led by Abel Mendez at the University of Puerto Rico proposed a new explanation: that a flare from a magnetar, a neutron star with a magnetic field 1 trillion times stronger than Earth's, may have slammed into a cold hydrogen cloud, causing it to emit a maser-like burst at exactly the hydrogen frequency. It would be a rare astrophysical event that wasn't even theoretically conceivable in 1977, when magnetars hadn't yet been discovered. The Mendez team calls their paper a reopening of the case, not a closure of it. The wow signal remains the most compelling, unexplained radio transmission ever recorded from space. The universe occasionally screams. For a fraction of a millisecond, sometimes less, a source somewhere in deep space releases more energy than the sun produces in days, concentrated into a single pulse of radio waves. These are called fast radio bursts, and since the first one was identified in 2007, they have gone from puzzling anomaly to one of the most active fields in astrophysics. The energy in a single FRB can outshine an entire galaxy, at least briefly. They arrive from every direction in the sky, which means they're extragalactic, coming from billions of light years away. Most are one-off events, flashing once and never repeating. A small fraction repeat, sometimes in irregular bursts, sometimes in patterns that hint at an orbital or precessional period. The leading explanation is magnetars, the same hypermagnetized neutron stars proposed for the WOW signal. And this was strengthened in 2020 when an FRB-like burst was detected from a known magnetar inside our own Milky Way, the first time we caught one in the act. But a 2025 study threw a complication into this picture. A bright FRB was traced to an ancient, quiescent elliptical galaxy, the kind of place where there should be no young active magnetars, because the galaxy's star formation ended billions of years ago. If magnetars require young, recently formed stellar environments, why are some FRBs coming from dead galaxies? In 2025, astronomers detected the brightest FRB ever recorded, nicknamed RBFLOAT, or radio brightest flash of all time, originating from a galaxy 130 million light years away. The source remains unidentified. We may be detecting multiple different phenomena under the same name, and the full taxonomy of what's producing these bursts is still being written. In the early 1960s, astronomers were puzzled by point-like objects in the sky that emitted enormous amounts of radio energy but looked like faint stars through optical telescopes. When their light was analysed, it turned out to be redshifted so enormously that these objects were at vast cosmological distances, billions of light years away. For them to be visible at all from such distances, they had to be producing energy on a scale previously unimaginable. They were named quasars, short for quasi-stellar objects. We now know what quasars are: the active cores of galaxies in which a supermassive black hole is devouring enormous quantities of infalling gas. As material spirals into the black hole, it heats to billions of degrees and blasts out radiation, sometimes more light than an entire galaxy of hundreds of billions of stars. A quasar can outshine its host galaxy by a factor of 1,000. What remains mysterious is how some of the most luminous quasars reach such extraordinary masses so early in the universe's history. JWST has observed quasars powered by black holes containing 1 billion or more solar masses within the first billion years of the universe's existence. Building that much mass through normal accretion, the slow accumulation of surrounding gas, shouldn't be possible in that time frame, even with constant feeding. The seeds these black holes grew from must have been unusually large, or the process of growth was somehow radically faster than our models allow. Neither explanation has a compelling theoretical basis yet. At the center of virtually every large galaxy sits a supermassive black hole, which are objects ranging from millions to tens of billions of times the mass of our Sun. The one at the center of the Milky Way, called Sagittarius a star, weighs in at about 4.3 million solar masses. The largest known, at the center of the galaxy TON 618, exceeds 66 billion solar masses. How these objects formed is one of the deepest unsolved problems in astrophysics. Stellar black holes, the kind that form when massive stars collapse, typically reach a few tens of solar masses. To get from there to millions or billions requires either an enormous amount of time and a constant food supply, or a different formation pathway entirely. Several possibilities are under investigation. One is the direct collapse of primordial gas clouds in the early universe, before the first stars formed, which could have created seed black holes of perhaps 100,000 solar masses in a single event. Another involves population 3 stars, the first generation of stars, which were likely far more massive than anything that forms today, potentially collapsing directly into black holes of thousands of solar masses. A third pathway involves the merger of many stellar black holes in the dense centers of early star clusters. The existence of billion solar mass black holes less than 700 million years after the Big Bang, revealed by JWST, suggests that whatever the formation mechanism was, it worked fast. Our current models are strained to explain it. In 1950, physicist Enrico Fermi was having lunch at Los Alamos when the conversation turned to recent reports of UFOs. Fermi listened for a while, then asked a question that has echoed through astrophysics ever since. Where is everybody? The logic is straightforward. The Milky Way alone contains more than 200 billion stars. Many of them have planets. Many of those planets are in habitable zones where liquid water can exist. The galaxy is about 13.6 billion years old, time enough for civilizations to have arisen, developed technology, and colonized the entire galaxy several times over, even at a fraction of the speed of light. And yet, there is no sign of them. This is the Fermi paradox, and it has produced a library's worth of proposed resolutions. Perhaps life is simply vanishingly rare, a cosmic accident that happened once, here, and nowhere else. Perhaps civilizations arise but inevitably destroy themselves before reaching spacefaring capability. Perhaps interstellar travel is fundamentally impossible in ways we don't appreciate. Perhaps advanced civilizations go quiet deliberately, avoiding contact for reasons we can't anticipate. Perhaps we've been listening in the wrong way, or on the wrong frequencies. The Great Filter hypothesis suggests that somewhere in the chain from simple chemistry to spacefaring civilization, there is a near impossible bottleneck. And the central question is whether that filter is behind us or ahead of us. If it's behind us, if the hard part is getting from non-life to life, or from single cells to complex organisms, then we may be rare but safe. If the filter is ahead, every other civilization faces it too, and our odds of long-term survival are grim. The search for life elsewhere has become more sophisticated. JWST is now characterizing the atmospheres of exoplanets in detail for the first time. In 2023, it detected the tentative signature of dimethyl sulfide in the atmosphere of K2-18b, a sub-Neptune planet in the habitable zone of a cool red dwarf star 120 light-years away. Dimethyl sulfide, on Earth, is produced only by marine phytoplankton. The detection was preliminary and contested. The signal was at the edge of detection confidence, and alternative non-biological chemistry cannot be ruled out. But the fact that we now have a telescope that can detect biologically relevant molecules in the atmospheres of planets orbiting other stars is a genuine watershed moment. If life is found on another world, even microbial, even just a chemical hint, the Fermi paradox becomes vastly more pressing. Life arising twice in the same galaxy would suggest it arises wherever conditions permit, which would make the silence deafening. If life never arose independently elsewhere, the silence makes sense. The answer either way will be one of the most profound findings in human history. JWST is now doing exactly this work. The data will either begin to answer the life question or make the silence more deafening. The cosmic microwave background is the universe's oldest light, radiation emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely for the first time. It fills the entire sky at a nearly uniform temperature of 2.7 degrees above absolute zero. Nearly uniform, but not perfectly so. There are tiny fluctuations, seeds of the large-scale structure that would later become galaxies and galaxy clusters. Within those fluctuations, there is one anomaly that has refused to be explained for more than 2 decades. A region in the southern sky, centered on the constellation Eridanus, that is measurably colder than everything around it, about 70 microkelvin below the CMB average, and spanning roughly 10 degrees across. That doesn't sound like much, but statistically, a cold spot of that size and depth shouldn't exist in the standard model. It's too big and too cold to be accounted for by random chance. The leading hypothesis for years was that the light crossed a supervoid, a vast, nearly empty region of space where galaxies are sparse, which would cause the light to lose energy. Surveys have found evidence of a large void in that direction, but most analyses suggest it's not quite deep enough or large enough to explain the full effect. An alternative, more exotic explanation is that the cold spot is the imprint of a collision with another universe. A bubble universe from the multiverse that briefly pressed against our own in the earliest moments and left a bruise in the microwave background. This is scientifically testable in principle, though confirming it would require a signature that current data may not yet provide. The cold spot remains one of the most discussed anomalies in modern cosmology. When cosmologists mapped the cosmic microwave background in high resolution, using NASA's WMAP satellite and later ESA's Planck mission, they expected the temperature fluctuations to be random, scattered uniformly across the sky with no preferred direction. Instead, they found something startling. The larger scale patterns in the CMB, these so-called quadrupole and octupole moments, appear to be aligned with each other and with the plane of our solar system. This alignment became known, partly tongue-in-cheek, as the axis of evil. It's a problem because the cosmological principle, a foundational assumption of modern cosmology, states that on large scales, the universe has no special directions. It looks the same from everywhere, in every direction. The axis of evil seems to say otherwise. The largest features of the early universe appear to know about the orientation of our solar system. The most likely explanation is that the alignment is a measurement artifact, contamination from our galaxy's own radiation that wasn't perfectly subtracted during data processing. Multiple groups have worked to clean the data more carefully, and the alignment has weakened somewhat under scrutiny, but it hasn't disappeared entirely. A minority of cosmologists take it seriously as evidence that the universe has a large-scale structure or anisotropy that our standard model doesn't account for. If the axis of evil is real, it would require a fundamental revision of cosmology. If it's noise, it's the most unsettling noise in the history of astronomy. Right now, the Milky Way, along with thousands of other galaxies in our local region of space, is hurtling through the universe at about 600 kilometers per second toward something in the direction of the constellation Centaurus. Something massive enough to pull all that matter across hundreds of millions of light years. Something we couldn't see for decades because it sits almost directly behind the densest part of our own galaxy's disk, where dust and gas block our view completely. This hidden gravitational anomaly is called the Great Attractor. It lies about 250 million light years away, and astronomers have gradually pieced together its nature using X-ray telescopes, radio telescopes, and infrared observatories that can peer through the galactic plane where optical light cannot penetrate. What they found is a concentration of galaxy clusters in an overdense region, with the Norma cluster as a major component, that is itself embedded in a larger superstructure sometimes called the Laniakea supercluster, of which the Milky Way is a far outlying member. But the Great Attractor isn't the only thing pulling on us. Beyond it, an even larger concentration called the Shapley supercluster, 650 million light years away, exerts its own pull. The details of this cosmic tug-of-war are still being mapped. And because the dark energy that's accelerating the universe's expansion works against gravity at cosmological scales, neither the Great Attractor nor the Shapley supercluster will ever consume us. We're falling towards something we'll never reach. When NASA launched the Pioneer 10 and Pioneer 11 spacecraft in the early 1970s, nobody expected they'd still be detectable decades later. Pioneer 10 was the first spacecraft to travel through the asteroid belt and the first to fly past Jupiter. Pioneer 11 followed, becoming the first craft to reach Saturn before heading out of the solar system in the opposite direction. By the 1980s and 1990s, engineers tracking these spacecraft with extraordinary precision noticed something odd. Both probes were decelerating very slightly, more than they should be, given the known forces acting on them. The discrepancy was tiny, on the order of 10 to the power of negative 10 meters per second squared. But it was real and consistent across both spacecraft, and it lasted for decades. It became known as the Pioneer anomaly, and for a while it attracted serious attention as possible evidence of new physics, a flaw in Newton's gravitational law at very large distances, or a hint of exotic forces. The answer, when it came in 2012, turned out to be more mundane but no less interesting as a lesson in careful measurement. The spacecraft were emitting thermal radiation, heat from their onboard radioisotope power systems, unevenly. More heat was escaping from one side than the other, creating a tiny but persistent thrust in one direction. When this was accurately modeled using recovered engineering documents and thermal physics calculations, it accounted precisely for the anomalous deceleration. The Pioneer anomaly was solved, but it's important to discuss because it shows how carefully the universe forces us to think before accepting exotic explanations. And because for 15 years, it genuinely could not be explained. In 1967, graduate student Jocelyn Bell Burnell noticed something strange in her radio telescope data. A signal that pulsed with such clockwork regularity, once every 1.33 seconds, that her supervisor, Anthony Hewish, initially labeled the source LGM1 for Little Green Men. The joke only half landed. Nothing natural was supposed to be that precise. The source turned out to be a pulsar, a neutron star spinning at extraordinary speed and emitting beams of radio waves from its magnetic poles. Every time the beam sweeps past Earth, we catch a pulse. Some pulsars spin hundreds of times per second, keeping time with a precision that rivals atomic clocks. The fastest known, called millisecond pulsars, complete more than 700 rotations per second. pulsars have become extraordinarily useful tools. Arrays of them across the galaxy act as a kind of natural gravitational wave detector. Tiny distortions in the fabric of space-time cause measurable shifts in the pulse arrival times. In 2023, the North American Nanohertz Observatory for Gravitational Waves, along with similar collaborations on other continents, reported detection of a gravitational wave background using exactly this technique. A low hum permeating the entire universe, likely generated by thousands of merging supermassive black hole pairs. But deep mysteries remain. How exactly a pulsar generates its beamed emission, the precise physics of the magnetosphere and the radiation process is not fully understood. And the existence of pulsars in globular clusters, where stars are ancient and the kind of high-mass stars that form neutron stars shouldn't have formed recently, suggests recycling processes in binary systems that we're still piecing together. Physics has a peculiar relationship with time. Newton treated it as an absolute backdrop, a universal clock, ticking at the same rate everywhere. Einstein revealed that time is relative. It passes more slowly in strong gravitational fields and at high speeds. GPS satellites, sitting in weaker gravity and moving fast, have to account for both effects simultaneously, or navigation errors would accumulate at about 11 kilometers per day. But here's what the equations don't explain. Why does time flow in one direction? The fundamental laws of physics, both classical and quantum, are mostly time symmetric. Run the equations of a billiard ball collision backward, and they still make sense. Run the equations of electromagnetism in reverse, and they still work. Yet in the macroscopic world, time clearly has a direction. Broken glass doesn't spontaneously reassemble. Heat flows from hot to cold, never the reverse. Cause precedes effect. The conventional answer is the second law of thermodynamics. Entropy, the measure of disorder in a system, always increases in closed systems. Time flows in the direction of increasing entropy. But this raises a deeper question. Why was entropy so low in the early universe to begin with? A low entropy starting state seems to require an explanation of its own, and finding one requires grappling with the origin of the universe. Some physicists argue time is not a fundamental feature of reality at all, that it emerges from deeper, timeless quantum processes. What those processes are, nobody can say. In September 2015, a century after Einstein predicted their existence, gravitational waves were directly detected for the first time by LIGO, two L-shaped detectors in Louisiana and Washington state, so sensitive they could detect a distortion of space-time smaller than 1/10,000th the diameter of a proton. The signal came from two black holes merging 1.3 billion light-years away. Since then, dozens of gravitational wave events have been recorded, merging black holes, merging neutron stars, and in November 2024, a gravitational wave event designated S2411125N that was immediately followed by a gamma-ray burst 11 seconds later, a combination that should be impossible under current theory, since black hole mergers were thought to produce no electromagnetic signal at all. The current hypothesis is that the merger occurred inside the disk of an active galactic nucleus, where surrounding gas provided fuel for a jet. The frontier now is detecting gravitational waves from the Big Bang itself. Cosmic inflation should have produced a background of primordial gravitational waves, ripples in space-time stretching from the earliest moments of the universe. These would show up as a specific pattern in the polarization of the cosmic microwave background, called B modes. Detecting them would be the most direct evidence we have ever obtained about the inflationary epoch and the energy scale at which it occurred. The Simons Observatory in Chile and future experiments in space, including LISA, the Laser Interferometer Space Antenna, planned for the 2030s, are designed to push into this territory. What they find will either confirm inflation or demand something entirely new. In 2016, astronomers Konstantin Batygin and Mike Brown announced something that reignited planetary science: mathematical evidence for an undiscovered planet in the outer solar system. Several distant objects in the Kuiper belt, the frozen debris field beyond Neptune, orbit the Sun in ways that are statistically improbable unless something massive is shepherding them. Their orbits are clustered, tilted, and elongated in a pattern that computer models suggest could be caused by a planet roughly 5 to 10 times Earth's mass, orbiting at several hundred times Earth's distance from the Sun. If Planet 9 exists, it would take between 10,000 and 20,000 years to complete a single orbit. It would be so far away and receive so little sunlight that it would be extraordinarily dim, which is why no direct observation has confirmed it yet. Multiple sky surveys have searched for it without success, though the searched area is enormous. Skeptics argue the clustering of Kuiper belt objects may be a selection bias, that the orbits appear clustered only because we've observed the ones easiest to see, which happen to be in certain directions. The Nancy Grace Roman Space Telescope, expected to conduct a sweeping survey of the sky in the late 2020s, should either find Planet 9 or make the selection bias argument more compelling. For now, the outer solar system may harbor a world larger than Earth that we've never seen. Ordinary matter, the protons and neutrons that make up everything we can see, is called baryonic matter by physicists. According to the standard cosmological model, the Big Bang produced a certain quantity of it. We can infer that total from the cosmic microwave background and from the abundance of light elements like hydrogen, helium, and lithium that were forged in the first few minutes. We know how much baryonic matter the universe should contain. The problem is, we can only account for about 2/3 of it. Stars, gas and dust in galaxies account for roughly 1/3. Another third appears to sit in the warm gas between galaxies and filaments of the cosmic web. But a substantial fraction, perhaps 1/3 of all ordinary matter in the universe, seems to be missing. The leading hypothesis is that the missing baryons reside in the warm-hot intergalactic medium, known as the WIM, a diffuse, hot gas at temperatures between 100,000 and 10 million degrees that pervades the cosmic web's filaments and voids. It is extraordinarily difficult to observe, because at those temperatures it emits mostly in the ultraviolet and X-ray range, and at such low densities the signal is faint. Several X-ray observatories have found hints of it along specific lines of sight, and future missions like Athena are specifically designed to map it. For now, roughly 1/3 of all the normal matter the universe is supposed to contain has no definitive address. The Milky Way is a living galaxy, still forming stars at a rate of a few solar masses per year, still growing, still active. But many of the largest galaxies in the universe are not. They are red and dead, entirely composed of old, red stars with no cold gas, no ongoing star formation, no future. They formed the bulk of their stars in a furious burst billions of years ago, and then simply stopped. How a galaxy quenches its star formation is one of the most studied and least resolved questions in galaxy evolution. Simply running out of gas isn't enough. Galaxies are constantly accreting new gas from the cosmic web around them. Something must actively shut off the supply, expel the existing gas, or heat it to a point where it can't cool and collapse into new stars. The leading suspects are active galactic nuclei, the supermassive black holes at galactic centers that, when actively feeding, blast enormous amounts of energy and radiation into the surrounding galaxy. This AGN feedback can drive galaxy-scale outflows of gas at thousands of kilometers per second, stripping the fuel supply faster than it can be replenished. But the details of exactly how AGN feedback operates, how it couples to the surrounding gas, and why it seems to work so efficiently in some galaxies and not others, are areas of intense active research. The connection between the mass of a galaxy's central black hole and the properties of its stellar population, tighter than it has any right to be, suggests the two are deeply linked in ways we haven't fully explained. The Big Bang nucleosynthesis model is one of the triumphs of modern cosmology. In the first 3 minutes after the Big Bang, the universe was hot enough for nuclear fusion, and it forged the light elements, hydrogen, helium, and tiny amounts of lithium. The predictions of this model match observations of hydrogen and helium abundances to extraordinary precision. Lithium-7, however, does not cooperate. The model predicts that primordial lithium-7 should be about 3 times more abundant than what is actually observed in the oldest, most metal-poor stars. Stars so ancient they formed from almost pure Big Bang material. These stars are the best available record of what the universe produced in its first moments, and they consistently show lithium abundances a factor of 3 below what theory says. Possible explanations include physics not captured by the standard model, new particles or interactions that would have destroyed some of the lithium-7 before stars formed. Another possibility is that the oldest stars have somehow processed their lithium inward, hiding it in their interiors rather than displaying it in their outer layers. Some researchers have proposed nuclear reaction rates that were used in the original model are slightly wrong. None of these proposals has been definitively confirmed, and the lithium problem remains a small but stubborn crack in our picture of the early universe. A black hole is a region of space-time where gravity is so strong that nothing, not matter, not light, not information, can escape once it crosses the event horizon. We can observe their effects on surrounding matter and space. We can detect the gravitational waves they produce when they merge. We have even imaged the shadows of their event horizons. But what happens inside one remains entirely beyond our ability to observe. General relativity predicts that at the center of a black hole lies a singularity, a point of infinite density where the equations break down completely. Most physicists believe singularities are not real features of the universe, but rather symptoms of a theory being pushed beyond its range of validity. A complete quantum theory of gravity would presumably replace the singularity with something physically meaningful, but we don't have such a theory. The deeper problem is the black hole information paradox, stated by Stephen Hawking in 1976. Quantum mechanics says that information is never truly destroyed. The state of a system is always recoverable in principle from its evolution. But if matter falls into a black hole, and the black hole eventually evaporates via Hawking radiation, where does the information about what fell in go? Hawking radiation is purely thermal. It carries no information about the original infalling material. If the information is truly lost, quantum mechanics is violated. If it somehow escapes in the radiation, it must do so by a mechanism entirely unknown. In 2012, physicist Ahmed Al-Mehri and colleagues published a paper arguing that the three things every physicist assumed to be true about black holes, which are unitarity, which states information is preserved, equivalence principle, which states an infalling observer feels nothing special at the horizon, and the validity of quantum field theory far from the horizon, are mutually contradictory. At least one of them must be wrong. This became the firewall paradox, suggesting that the event horizon might be surrounded by a wall of high-energy radiation that incinerates anything crossing it, rather than being the unremarkable boundary general relativity describes. If the firewall exists, it violates the equivalence principle, one of Einstein's foundational insights. If it doesn't, information is lost and quantum mechanics breaks down. This paradox has occupied some of the sharpest minds in theoretical physics for nearly 50 years without resolution, and the firewall debate remains unresolved more than a decade after it was posed. If cosmic inflation is real and eternal, if it continues generating new bubble universes endlessly, then our entire observable universe, with its 100 billion galaxies and 13.8 billion years of history, is just one pocket in a vast, perhaps infinite froth of disconnected universes. This is the inflationary multiverse. Each bubble universe in this framework could have different physical constants, a different value for the electron mass, a different strength of gravity, a different cosmological constant. Most of these universes would be sterile, collapsing or expanding too fast for stars to form. We live in one that permits stars, planets, chemistry, and life, because those are the conditions necessary for us to exist, to ask the question. This reasoning, known as the anthropic principle, makes cosmologists uncomfortable, because it seems to replace a scientific explanation with a selection effect. We can't observe the other universes. We have no way to test whether they exist. Inflation predicts them, but inflation itself predicts many different outcomes depending on the specific model, making it difficult to falsify. Critics argue that a theory which predicts everything predicts nothing. String theory adds another layer. The string theory landscape, a space of perhaps 10 to the power of 500 possible configurations of extra dimensions and physical constants, each corresponding to a different possible universe. If the multiverse is real and populated by all these configurations, then perhaps the laws of physics in our universe are not fundamental, but contingent. not derived from necessity but drawn from a vast cosmic lottery. What would it mean to explain a universe whose properties are accidents? When a star between about 8 and 20 times the mass of the Sun reaches the end of its life, its core collapses catastrophically. The implosion is so violent that electrons are forced into protons, creating neutrons, and the resulting object, a neutron star, packs roughly 1.4 solar masses into a sphere about 20 kilometers across. A teaspoon of neutron star material would weigh about 1 billion tons. The density at the core of a neutron star exceeds anything achievable in a laboratory, anywhere on Earth, by many orders of magnitude. At such pressures, matter may exist in states with no equivalent in ordinary physics. Some models predict that neutrons dissolve into their constituent quarks, creating a quark-gluon plasma at the core. Others suggest exotic particles called hyperons, containing the strange quark, may form. Others propose a state called strange quark matter, which would be the densest stable form of matter possible. The equation of state of neutron star matter, the relationship between pressure, density, and temperature inside one, is genuinely unknown. Gravitational wave detections of neutron star mergers, like the landmark event GW170817 in 2017, provide some constraints. The way neutron stars deform as they spiral together reveals something about their stiffness, which depends on their internal structure. The NICER telescope on the International Space Station is measuring neutron star radii with increasing precision to constrain the equation of state further. GW170817 was exceptional because it was detected simultaneously in gravitational waves and across the entire electromagnetic spectrum, from gamma rays to radio waves. The gravitational wave signal lasted 100 seconds and revealed that the two neutron stars had radii between about 11 and 13 kilometers, constraining the stiffness of nuclear matter at extreme densities. But the fate of the merged remnant, whether it collapsed immediately into a black hole or briefly survived as a hypermassive neutron star before collapsing, could not be determined from the available data, because the expected gravitational wave signal from the post-merger remnant at frequencies above a few kilohertz was just beyond the sensitivity of LIGO and Virgo at the time. Future detectors with improved high-frequency sensitivity are specifically designed to catch this post-merger signal. What they find will directly constrain what happens at the most extreme densities in nature, and possibly tell us whether quark matter exists in the real universe, or whether the cores of neutron stars remain a form of nuclear matter we've never replicated in any experiment. Dark energy, in its most commonly accepted formulation, is the cosmological constant, a fixed energy density belonging to empty space itself. Einstein introduced it in 1917 to keep his equations from predicting a dynamic universe. Today it's back, and apparently necessary. The problem is the number. Quantum field theory, when it calculates the energy density of the vacuum, the energy inherent in empty space due to quantum fluctuations, produces a number vastly larger than the observed cosmological constant. Exactly how much larger is a matter of how you set up the calculation, but the discrepancy is somewhere between 60 and 120 orders of magnitude. 120 orders of magnitude is a number so astronomically wrong that it has been called the worst prediction in physics. Something must be cancelling almost all of the predicted vacuum energy, leaving only the tiny residue we observe as dark energy. But what? No known mechanism produces this cancellation without fine-tuning the parameters to unreasonable precision. Supersymmetry, which pairs every known particle with a partner particle, would have provided an elegant cancellation. But the Large Hadron Collider found no evidence of supersymmetric particles at the energies where they were expected. String theory's landscape might explain it anthropically, but that loops us back to the multiverse problem. The cosmological constant problem is often described as the greatest unsolved problem in theoretical physics. It has been called a theoretical crisis, and no resolution is in sight. For fractions of a second to several minutes, somewhere in the distant universe, a burst of gamma rays flashes with more energy than the sun will emit over its entire lifetime. These are gamma ray bursts, and they were first detected by military satellites in the late 1960s. Satellites designed to monitor for nuclear weapon tests, which are also sources of gamma radiation. What the satellites found instead were bursts coming from deep space, with no obvious explanation. We now understand the broad outlines. Short gamma-ray bursts, lasting less than 2 seconds, are caused by the merger of two neutron stars, or a neutron star and a black hole. Long gamma-ray bursts, lasting more than 2 seconds, are associated with the deaths of massive, rapidly spinning stars, whose collapsing cores generate jets of material moving at near light speed. What remains mysterious is the detailed physics. How exactly is the enormous energy channeled into such narrow, relativistic jets? What determines whether a jet punches through the stellar material or gets smothered? In 2024, the newly launched Einstein probe detected an explosion that matched neither the short nor long category, suggesting a new class of gamma-ray burst may exist. And the November 2024 event, S241125N, a gravitational wave from a black hole merger immediately followed by a gamma-ray burst, broke the assumption that purely black hole mergers produce no electromagnetic counterpart, suggesting that our categories are not complete. The most energetic events in the universe are still being classified. A spiral galaxy is one of the most beautiful structures in the universe. From M51, the Whirlpool Galaxy, to our own Milky Way, spiral arms sweep outward from a central core in graceful curves, highlighted by young blue stars and glowing nebulae. They are elegant, organized, and deeply puzzling. The problem is that spiral arms shouldn't last. A galaxy rotates, but not like a solid object. The inner parts orbit faster than the outer parts, because they're closer to the center's gravity. If the spiral arms were fixed structures made of the same stars, the differential rotation would wind them up into a featureless disk in a relatively short time, far less than the age of a typical galaxy. Yet spiral arms persist for billions of years. Why? The currently accepted answer is density wave theory, first developed in the 1960s. In this picture, the spiral arms are not made of fixed stars, but are regions of higher density, like a traffic jam on a circular road where cars slow down, pile up briefly, then continue. Stars pass in and out of the arms as the galaxy rotates. The arms themselves propagate as waves through the galactic disk. But density wave theory has weaknesses. In some galaxies, the arms appear too ragged and fragmented to be explained by simple waves. In others, the pattern speeds of the arms and the disk rotation don't match predictions cleanly. Tidal interactions with companion galaxies complicate the picture further. The exact mechanics of how spiral structure forms is sustained, and why it varies so dramatically from galaxy to galaxy remain active problems. About 25 light-years from Earth, the bright star Fomalhaut hosts one of the most discussed and debated objects in the history of exoplanet research. In 2008, the Hubble Space Telescope captured an image of a point of light at the edge of Fomalhaut's debris disk, a ring of icy rubble analogous to our own Kuiper belt. The object moved over successive years in a way consistent with a planet in a wide orbit, and it was hailed as the first directly imaged exoplanet in visible light. Then it started behaving strangely. By 2014, the object had grown more diffuse and dimmer. By around 2020, it had essentially disappeared. A genuine planet cannot dissolve. Planets are gravitationally bound objects. What had been seen was something else. The current interpretation, developed after extensive analysis, is that the Hubble observations captured the expanding debris cloud from a massive collision between two large objects, planetesimals, in Fomalhaut's disk. The cloud was initially dense enough to reflect enough light to appear as a point source, then spread and faded as it expanded. It's a remarkable natural event to have caught in action, but what it tells us about Fomalhaut's disk, the frequency of such collisions, the population of objects that cause them, whether a genuine planet lurks nearby, driving the debris ring's sharp inner edge, remains uncertain. Fomalhaut B was never a planet. What it was is still being sorted out. Every second, high-energy particles, protons and atomic nuclei, rain down on Earth's atmosphere from every direction in the sky. Some of them arrive with energies so extreme that their origin cannot easily be explained. The most energetic cosmic rays ever recorded carry kinetic energies comparable to a professionally thrown baseball, concentrated into a single subatomic particle. They hit the upper atmosphere and cascade into showers of secondary particles that spread across kilometers at ground level. At such energies, cosmic rays should not be able to travel far across the universe. High-energy protons interact with the cosmic microwave background, producing pion particles and losing energy. A process known as the GZK limit, after Greason, Zatsepin, and Kuzmin, who predicted it in 1966. Particles above this limit should lose most of their energy within about 100 million light-years of their source. This means the most energetic cosmic rays observed must come from relatively nearby on cosmological scales. But no obvious local sources match their arrival directions. Lower energy cosmic rays are generally traced to supernova remnants within the Milky Way, which accelerate particles through repeated bouncing across magnetic shock fronts. But the highest energy particles defy neat explanations. Active galactic nuclei, gamma ray bursts, and even the Great Attractor region have been proposed as accelerators. In 2017, the Pierre-Auger Observatory found a statistically significant correlation between the highest energy cosmic ray arrival directions and the positions of nearby active galactic nuclei, suggesting those sources play a role. But the association is not tight enough to identify specific sources for specific events. The most energetic particles in the universe have no confirmed birthplace. General relativity describes gravity as the curvature of space-time caused by mass and energy. Quantum mechanics describes the behavior of matter and energy on the smaller scales as probabilistic, discrete, and fundamentally uncertain. Both theories are extraordinarily successful within their own domains. Together, they are incompatible. When physicists try to apply quantum mechanics to gravity, to quantize it the way they've quantized electromagnetism and the strong and weak nuclear forces, the equations produce infinities that can't be removed. The mathematical machinery that works for other forces fails for gravity. This is not a minor technical inconvenience. It represents a fundamental incompatibility between the two pillars of modern physics. The most developed attempt at a resolution is string theory, which proposes that all particles are tiny, vibrating strings of energy, and that the different modes of vibration produce what we observe as different particles, including the hypothetical graviton, the carrier of gravity. String theory naturally incorporates quantum gravity, and has produced remarkable mathematical structures. It also requires 6 or 7 additional compact dimensions of space beyond the 3 we experience, and it has yet to produce a testable prediction that has been confirmed. Loop quantum gravity takes a different approach, quantizing space itself into discrete units. Loops of space-time at the Planck scale, about 10 to the power of -35 meters. Both approaches remain mathematically incomplete and experimentally unconstrained. A theory of quantum gravity, one that reconciles the two great frameworks of modern physics, is the deepest theoretical goal of fundamental physics. It is not yet achieved. The universe on its largest scales is not a uniform sea of matter. It is a cosmic web, an intricate network of filaments, sheets, voids, and nodes that spans the observable universe. Filaments are vast, thread-like structures hundreds of millions of light-years long, composed of dark matter and hot gas, with galaxies strung along them like beads. Where filaments intersect, vast clusters of hundreds or thousands of galaxies congregate. Between them lie enormous voids, regions nearly empty of galaxies, spanning hundreds of millions of light-years in every direction. This structure grew from the quantum fluctuations of inflation, amplified over 13.8 billion years by gravity. The general architecture was predicted by cosmological simulations in the 1980s, and observations have confirmed it in remarkable detail. Projects like the Sloan Digital Sky Survey and DESI have mapped tens of millions of galaxies, revealing the web's structure across enormous volumes. What remains mysterious is the detailed physics of the small scales within the web. Simulations of cosmic structure formation predict many more small dwarf galaxies around large galaxies like the Milky Way than we actually observe, the missing satellites problem. They also predict that dwarf galaxies should have dense, cuspy cores of dark matter, but observations suggest the cores are flatter, the core cusp problem. These discrepancies may reflect interactions between dark matter and ordinary matter that simulations don't capture, or they may hint at a different nature for dark matter than the cold, collision-free variety usually assumed. The Webb's skeleton is mapped. Its detailed physics is not. When cosmic ray particles strike the upper atmosphere, they produce showers of secondary particles, including positrons, the antimatter counterparts of electrons. In 2008, the Pamela satellite detected far more high-energy positrons arriving from space than the standard model of cosmic ray propagation predicted. The AMS-02 detector on the International Space Station confirmed this success in greater detail from 2013 onward, showing that the positron fraction rises sharply above about 10 gigaelectronvolts of energy. The excess positrons need a source. The two leading explanations are both extraordinary. One is that pulsars, rapidly spinning neutron stars, are injecting positrons into space when their powerful magnetic fields create electron-positron pairs. Several nearby pulsars have the right age and properties to be candidates. The other explanation is dark matter annihilation. If dark matter particles are their own antiparticles, then when two of them collide, they might annihilate and produce, among other things, positrons at exactly the energies observed. The HAWC and HESS gamma-ray observatories have now measured the halos of high-energy particles around the most promising candidate pulsars. And the energy losses in those halos suggest the pulsars may not be leaking particles efficiently enough to reach Earth in the required quantities. This actually keeps the dark matter interpretation alive as a possibility. The positron excess has not been definitively explained. The universe at the moment the cosmic microwave background was emitted 380,000 years after the Big Bang was almost entirely smooth. There were slight overdensities and underdensities, but no stars, no galaxies, no sources of light beyond the cooling background glow. Then, over the next 100 million years or so, gravity pulled the overdense regions together, forming the first stars. This period is called cosmic dawn. The first stars, called population 3 stars, were unlike anything that exists today. They formed from pure hydrogen and helium, with none of the heavier elements that form in the nuclear furnaces of later stellar generations. Without those heavier elements to help cool collapsing gas clouds, the first stars are thought to have been massive, perhaps hundreds of times the mass of the Sun, and therefore short-lived, burning through their fuel in millions, rather than billions of years, and then dying in cataclysmic explosions that seeded the universe with the first heavy elements. No population 3 star has ever been directly observed. They should be too far away and too ancient to detect individually with current telescopes. JWST is searching for their signatures, both as extremely distant, primitive galaxies and as the chemical fingerprints they left in the gas composition of very early galaxies. In 2024, JWST found evidence for unusually metal-poor stellar populations in very early galaxies that may include population 3 stars, but no clean, unambiguous detection has been confirmed. As of 2026, the first stars remain hypothetical. Powerful theoretical entities whose predicted properties have not yet been directly verified. The Higgs field permeates all of space and gives mass to elementary particles. The Higgs boson, discovered at the Large Hadron Collider in 2012, is the quantum excitation of this field. The value of the field, its vacuum expectation value, determines the masses of all fundamental particles, including the stability of matter as we know it. Measurements of the Higgs boson's mass, combined with the mass of the top quark, place the Higgs field in a state that physicists call metastable. The current state of the field is not the lowest possible energy state. It's a local minimum, not a global one. In principle, through a quantum tunneling event, a region of space could decay from the current vacuum state to a lower energy state. This new vacuum would have different physical constants. The electron might have a different mass, atoms as we know them might not be stable. A bubble of lower energy vacuum, if it formed, would expand outward at the speed of light. There would be no warning. The bubble wall would simply arrive, and everything inside would be instantly restructured into a physics incompatible with the existence of chemistry, biology, or anything we recognize. The probability of this happening in any given year is extraordinarily small, far smaller than the probability of winning a lottery 1 trillion times in a row. On human timescales, it is effectively zero. But the universe is vast and old, and if even one such bubble has nucleated anywhere within our past light cone in the last 13.8 billion years, we would not be here to discuss it. Our existence may be evidence that we are either lucky or that new physics beyond the standard model stabilizes the vacuum in a way we haven't discovered yet. The geometry of space depends on the total energy density of the universe. If the density is above a critical value, space curves like the surface of a sphere. Below it, space curves like a saddle. At exactly the critical value, space is flat. Observations, particularly from the cosmic microwave background, tell us the universe is flat to extraordinary precision, within a fraction of a percent of the critical density. This is deeply strange. In the early universe, any small deviation from perfect flatness would have been amplified over time. If the universe had been even slightly above the critical density at 1 second after the Big Bang, it would have collapsed back on itself long before galaxies could form. If it had been slightly below, it would have expanded so fast that matter would never have condensed into structure. The universe's flatness today requires that its density at 1 second after the Big Bang was tuned to the critical value to at least 52 decimal places. This is called the flatness problem, and it is one of the primary motivations for cosmic inflation. An inflationary epoch would have stretched any initial curvature to such a vast scale that the visible universe would appear flat regardless of the global geometry. The same reason the Earth's surface looks flat on human scales, even though it's a sphere. Inflation naturally explains the flatness without requiring any fine-tuning. But it explains it by invoking an inflationary field whose origin and nature remain unknown. A solution that defers the mystery to a deeper layer is a real solution, but it's not a complete one. In 1978, physicist John Archibald Wheeler proposed a thought experiment that later became a real one. The delayed choice experiment. In the standard double-slit experiment, a single photon passes through 2 slits and creates an interference pattern on a detector screen. evidence that it traveled through both slits simultaneously as a wave. But if you add a detector at the slits to find out which one the photon went through, the interference pattern disappears, and the photon behaves as if it went through only one slit as a particle. Wheeler asked, "What if you wait until after the photon has passed through the slits to decide whether to look at which path it took? Can a choice made in the present affect how the photon behaved in the past?" The experiment has been performed, and the answer is disturbing. The photon's behavior at the slits is determined by the measurement choice made after it has already passed through them. There is no hidden story about which path the photon really took before the measurement. Quantum mechanics describes reality as fundamentally indeterminate until an observation is made, and it appears the past can be affected by measurements made in the present, at least in a quantum context. What this means for the nature of reality is deeply contested. Some physicists interpret it as evidence that there is no underlying reality independent of observation. Reality is created by measurement. Others argue for the many worlds interpretation, where every quantum event branches the universe into multiple histories. Others maintain that quantum mechanics is incomplete, that there must be a deeper description we haven't found yet. The debate has continued for a century and shows no sign of resolution. Neutron stars are already extraordinary. Compact balls of nuclear density matter that form in the aftermath of stellar explosions. But a subset of neutron stars are among the most violent objects in the observable universe. Magnetars have magnetic fields so intense that they dwarf anything else that exists. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. A magnetar's field is 1,000 times stronger still, roughly 10 to the power of 15 Gauss. At such intensities, the physics is extreme in ways that have no laboratory equivalent. The magnetic field is strong enough to distort the shape of hydrogen atoms, stretching them into thin cylinders aligned with the field. X-ray photons traveling through the magnetosphere split into 2 polarization modes with different speeds. The field itself contains so much energy that it can fracture the neutron star's solid crust, a starquake, generating explosions visible across the galaxy. The origin of such intense magnetic fields is not fully understood. One hypothesis is that they arise from a convective dynamo process during the neutron star's formation, a turbulent few seconds immediately after the supernova collapse, during which rapid convection and rotation could amplify magnetic fields exponentially. Another is that magnetars form preferentially from the most rapidly rotating progenitor stars, whose angular momentum gets converted to magnetic energy. The exact mechanism remains unclear, and the detailed structure of the magnetic field inside a magnetar, how it threads through the superconducting interior, is an active area of theoretical investigation. The universe is supposed to be roughly uniform on large enough scales. This is called the cosmological principle, the assumption that no region of the universe is specially different from any other when viewed from a sufficient vantage point. Models of cosmic structure suggest that above about 300 million light years, matter should be distributed without significant clumping. The problem is that astronomers keep finding structures that violate this expectation. The Sloan Great Wall discovered in 2003, is a filament of galaxies about 1.4 billion light-years long. The Hercules Corona Borealis Great Wall, identified in 2013 and subsequently studied in greater detail, appears to span roughly 10 billion light-years, a significant fraction of the observable universe. Clusters of gamma-ray bursts that seem to trace its structure span a region so large that, under the cosmological principle, they should not form a coherent structure at all. The giant arc, reported in 2021, is a crescent-shaped arrangement of galaxies and galaxy clusters, about 3.3 billion light-years across, discovered by Alexia Lopez at the University of Central Lancashire. And in 2023, the Big Ring, another circular arrangement of galaxies near the giant arc, was announced, spanning about 1.3 billion light-years. None of these structures fit comfortably into the standard model of cosmology. They are either statistical flukes, features that appear significant but arise from the enormous volume of the observable universe and the way we select survey areas, or they indicate that the universe has large-scale structure beyond what current models predict. The cosmological principle itself may need revision. All known outcomes for the universe are unpleasant. The question is which one applies. If dark energy remains constant, as the cosmological constant model assumes, the universe will continue expanding forever, with galaxies accelerating away from each other. Within a few tens of billions of years, galaxies beyond our local group will recede past our cosmological horizon and become permanently invisible. Stars will die and not be replaced. Over trillions of years, the universe will fade toward heat death, maximum entropy, no useful energy gradients, a cold and uniform darkness. This is sometimes called the Big Freeze. If dark energy strengthens over time, if it acts more like the phantom energy some models allow, the expansion could accelerate faster than the current expansion of space, eventually tearing apart structures on smaller and smaller scales. Galaxy clusters first, then galaxies, then solar systems, then planets, then atoms. This is the Big Rip, potentially occurring in as little as 20 to 200 billion years. If dark energy weakens or reverses, gravity could eventually overcome the expansion, causing the universe to collapse back on itself in a big crunch. This is currently considered unlikely based on observational data, but not impossible. The 2025 DESI results hint that dark energy may not be constant, that it may have been stronger in the past and weaker now, or varying in some other way. If confirmed, this rules out the simple cosmological constant model and opens the possibility of a significantly different future for the universe than the Big Freeze scenario most physicists have settled on. Everything about the end of the universe depends on understanding what dark energy actually is. And we still don't. In 2015, astronomer Tabitha Boyajian and colleagues reported the most unusual light curve ever recorded by the Kepler Space Telescope. KIC 8462852, quickly nicknamed Boyajian Star or Tabby Star, was dimming in patterns that nobody could explain. Most exoplanet transits cause smooth, shallow, regular dips in starlight. Tabby's star dimmed by up to 22% at irregular intervals, with light curves that were asymmetric, complex, and sometimes gradual rather than sharp-edged. Speculation quickly turned to megastructures. Physicist Freeman Dyson had theorized in 1960 that an advanced civilization might build a swarm of structures around their star to capture its energy output. Such a Dyson sphere or swarm would produce exactly the kind of complex, irregular dimming that Tabby's star showed. For a brief period, this was not merely a fringe idea. It was seriously discussed in the scientific literature as one possible explanation. The current most widely accepted explanation is circumstellar dust. Clouds of fine dust from disintegrating comets or planetesimals orbiting at different distances, producing the complex wavelength-dependent dimming patterns. Observations showed that the star dims more at shorter wavelengths, exactly what dust would do, since it scatters short wavelength light more effectively. A genuine solid object would block all wavelengths equally, but circumstellar dust covers a range of specific scenarios and the exact origin of the dust. What is producing it? What is disrupting it? And why Tabby's star seems to behave unlike any other star in this way is still not definitively established. It remains the most enigmatic star in the Milky Way. The Milky Way does not sit in a typical region of the universe. Our galaxy is located in a large, underdense region, a void that extends for roughly 1 billion light-years in several directions. This local void, sometimes called the KBC void after Keenan, Barger, and Cowie, who characterized it in 2013, contains about 20% less matter than the cosmic average. This matters for at least 2 reasons. First, galaxies in an underdense region would experience less gravitational braking from surrounding matter, meaning they recede from each other slightly faster than the universal average. This could mean our local measurements of the Hubble constant are slightly inflated, relative to the true global value, which might partially explain the Hubble tension. Studies published in 2025 reanalyzed decades of baryon acoustic oscillation data and found that a local void model can significantly reduce the tension between local and early universe measurements of expansion. Second, if our local neighborhood is substantially underdense, then the cosmological principle is violated at a scale that should already be uniform. 1 billion light-years is bigger than the scale at which uniformity is supposed to set in. Whether the local void is anomalously deep or simply within the normal range of cosmic variance is contested. If we are in a cosmic void, our view of the universe may be subtly skewed in ways that have influenced some of the most fundamental measurements in modern cosmology. Einstein's general relativity predicts that mass bends light. When a massive object, a galaxy, a cluster of galaxies, or a concentration of dark matter sits between us and a more distant source of light, the intervening mass acts as a lens, warping and sometimes multiplying the image of the background source. This gravitational lensing has become one of astronomy's most powerful tools, used to map dark matter distributions and study distant galaxies that would otherwise be too faint to detect. But lensing observations have produced some anomalies. One involves the clustering of matter measured through the gravitational shear of background galaxies, a statistic called S8. Measurements of S8 from the cosmic microwave background, using the Planck data, predict a universe that is more lumpy at small scales than what weak lensing surveys actually find when they directly measure the galaxy distribution. The discrepancy is at the 2 to 3 sigma level, not as dramatic as the Hubble tension, but persistent across multiple surveys. A second anomaly involves quasar lensing. When a quasar is gravitationally lensed by an intervening galaxy into multiple images, the time delay between the images, caused by the different path lengths of the light, can be used to measure the Hubble constant. These time delay measurements consistently favor the higher Hubble constant values obtained by Rees's team using Cepheids, deepening the puzzle rather than resolving it. Lensing is one of the few cosmological tools that doesn't rely on any assumed standard candle or ruler. The fact that it consistently agrees with one side of the Hubble tension is telling, but what exactly it's telling us remains to be seen. In October 2017, the Pan-STARRS telescope in Hawaii detected an object that had traveled from somewhere outside the solar system. The first interstellar object ever confirmed passing through. It was named Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. Astronomers scrambled to observe it before it escaped beyond telescope range, and what they found produced a debate that has not ended. Oumuamua was odd in multiple ways. Its shape, inferred from the way its reflected brightness changed as it tumbled, suggested an extreme aspect ratio, possibly 10 times longer than it was wide, or alternatively flat like a pancake. No known natural object forms this way. It was also highly reflective, consistent with a metallic or very smooth surface, rather than the dark, organic coated material typical of comets and asteroids from our own solar system. Most surprising was its trajectory. As Oumuamua moved away from the Sun, it accelerated slightly more than gravity alone could explain. The leading explanation for this non-gravitational acceleration in comets is outgassing, venting a volatile material that acts like a rocket. But no outgassing was detected from Oumuamua. No gas or dust cloud surrounded it. Several explanations have been proposed. Astronomer Avi Loeb of Harvard argued that Oumuamua's properties, the shape, the reflectivity, the non-gravitational acceleration, the absence of outgassing, were consistent with a thin artificial solar sail propelled by radiation pressure. Other researchers have proposed that Oumuamua was made of exotic hydrogen ice, which would sublimate invisibly, or that it was a fragment of a shredded planet from another star system, or a nitrogen ice chunk from a Pluto-like body. Every proposed natural explanation has weaknesses. None fits all the observed properties simultaneously. Oumuamua is gone, beyond reach, never to return. The second interstellar visitor, Borisov, detected in 2019, was a perfectly normal-looking comet. Oumuamua remains uniquely strange and uniquely unexplained. The moon is enormous relative to Earth. Of all the moons in the solar system, none other is as large compared to its host planet. The current best explanation for this is the giant impact hypothesis. Roughly 4.5 billion years ago, early Earth was struck by a Mars-sized body, named Theia, at a glancing angle. The impact was catastrophic, vaporizing a large portion of both bodies. The resulting debris disk of vaporized rock orbiting Earth gradually accumulated into the moon. This model explains several things well, including the moon's low iron content compared to Earth, the moon's lack of volatile elements, and the similar isotopic composition of Earth and moon samples. But high-precision measurements have revealed that the moon and Earth share isotopic compositions of oxygen, tungsten, and other elements to a degree that strains the standard model. If Theia was a separate body from a different part of the solar system, as expected, its material should have a different isotopic signature from Earth's, yet the moon looks almost identical to Earth. This has led to proposals of a high-energy, nearly head-on collision that thoroughly mix the two bodies' material, or even a multiple impactor scenario involving several smaller collisions. The moon's origin is generally agreed to involve a giant impact. The details of that impact, and why the moon looks so much like Earth, are still being actively debated. How fast does Saturn rotate? The question seems absurd. Surely we can look at a planet and measure how long it takes to spin. For most planets, this is straightforward. Track a surface feature. Saturn has no solid surface, and its cloud patterns are driven by winds rather than deep rotation. The best method astronomers have used is measuring Saturn's magnetic field, which is generated deep in the planet's interior and should rotate with the planet's bulk. But Saturn's magnetic field is strangely aligned almost perfectly with its rotational axis, unlike every other magnetized planet in the solar system, making it impossible to use field rotation as a clock. Cassini's observations gave different rotation periods for Saturn's northern and southern hemispheres, which is physically impossible for a single solid body, implying the observed periods reflect something about Saturn's atmosphere rather than its interior. The current best estimate for Saturn's interior rotation period is around 10 hours and 33 minutes, inferred from seismology by analyzing the vibrations of Saturn's rings, which the rings transmit like the strings of a musical instrument. But this estimate carries uncertainty, and the detailed structure of Saturn's deep interior, where the true rotation is anchored, remains unknown. Saturn's moon Iapetus presents its own puzzle. A ridge of mountains nearly 20 kilometers high, running almost perfectly along the equator, circling about half the moon's circumference. Mountains this tall on a body this small are structurally remarkable. They may be the remnant of a ring that once encircled Iapetus and collapsed inward when the moon's rotation slowed. But this requires a very specific early history for the moon that isn't definitively established. Magnetic fields are everywhere in the universe. Stars, planets, galaxies, and galaxy clusters all have them. The Earth's magnetic field protects life from solar radiation. The Milky Way's magnetic field stretches across the galaxy and influences cosmic ray propagation. Galaxy clusters have magnetic fields threading through the hot plasma between their member galaxies. The mystery is where these fields came from. The universe at the time of the cosmic microwave background showed no detectable magnetic field. Between then and now, the universe grew structured, and apparently, magnetic fields appeared throughout it. But the seed fields from which the large-scale cosmic fields grew must have been generated by some physical process in the early universe. Several mechanisms have been proposed. Inflation might have generated primordial magnetic fields through quantum fluctuations. Phase transitions in the early universe analogous to the way water turns to ice, but involving changes in the fundamental symmetries of physics, could have produced field seeds. First-generation stars and early supernovae could have magnetized surrounding gas, which was then spread by turbulence. In 2025, analyses of the cosmic microwave background and very high-energy gamma rays from blazars, active galactic nuclei whose jets point toward Earth, have placed constraints on intergalactic magnetic fields, finding evidence for extremely weak fields permeating the voids between galaxy filaments. These void fields would be the most pristine remnants of whatever primordial magnetogenesis process occurred. Their origin remains one of the least publicized but most fundamental puzzles in cosmology. It's worth stepping back to ask a question that underlies all of them. What if the framework itself is wrong? The standard model of cosmology, lambda CDM, assumes general relativity is correct on all scales, that dark matter is a particle that hasn't been detected yet, that dark energy is a property of space, and that the universe's large-scale structure is broadly consistent with the cosmological principle. Under those assumptions, the model works remarkably well at describing what we observe. But almost every cosmological mystery can be traced back to one of those assumptions. If dark matter behaves differently from our models, not cold, not collision-free, not a particle at all, the missing satellites problem and the Caucus problem go away. If general relativity is modified at large scales, as modified Newtonian dynamics, or MOND, proposes, then dark matter itself might not be needed to explain galaxy rotation curves, though MOND struggles to explain galaxy clusters without some form of dark matter. If the cosmological principle fails on billion light-year scales, as the giant structures suggest, then the entire foundation of how we model the universe needs revisiting. JWST has already revealed galaxies in the early universe that are too massive, too mature, and too structured to fit neatly into the standard hierarchical formation models. The Hubble tension, confirmed by 2 flagship telescopes, says the universe's expansion rate doesn't make sense. The DESI dark energy results suggest the universe's dominant energy component is not what we thought it was. There's also a growing tension in what cosmologists call the S8 parameter, the clustering amplitude of matter in the universe. Predictions from the Planck CMB data say the universe should be slightly more clumped at small scales than what weak gravitational lensing surveys actually observe when they look directly at the galaxy distribution today. This S8 tension has been present in multiple independent datasets, and while it's not yet at the dramatic significance of the Hubble tension, it's accumulating. 2 independent ways of measuring the same property of the universe persistently disagree, and the gap won't easily go away. These are not just data discrepancies, they may be cracks in the foundation. In the history of physics, cracks like these have sometimes been patched. Systematic errors identified, models adjusted, new particles added. But sometimes, the cracks opened into entirely new domains of knowledge. The anomalous perihelion of Mercury looked like a small measurement disagreement for decades before general relativity showed it pointed to a fundamentally different picture of gravity. The ultraviolet catastrophe in blackbody radiation looked like a technical problem before quantum mechanics dissolved it by replacing classical physics entirely. All of this might get resolved by filling in gaps within the current framework. New particles found, new mechanisms identified, new measurements that bring the numbers into agreement. Or the resolution might require something more radical. A new theory of gravity, a new picture of the early universe, a rethinking of what dark matter and dark energy actually are. The history of science includes chapters where the mysteries weren't solved. They were dissolved because the framework that generated them turned out to be wrong. Newtonian mechanics didn't explain the precession of Mercury's orbit. The puzzle dissolved when general relativity replaced it. Dark energy itself was the answer to a puzzle that nobody had thought to ask under the old framework. 50 questions, no complete answers. The universe is patient. It has answers to all of them. The question is whether we're clever enough to ask the right questions to get there. If this kind of thinking is what draws you here, subscribe. Every exploration starts with acknowledging how much remains unknown.